The example of updating the shared queue which we walked through just now illustrates a race condition. A race condition is said to occur when two or more threads read and write the same data concurrently, and the outcome depends on the particular order of accesses. The race conditions are also known as data races. The bugs that are typically caused by race conditions or data races, they are extremely nasty to detect and debug. Mainly because if you run the same multi-threaded program several times, most of the times you will see that your program works correctly. Only sometimes it doesn't. So for instance, in our previous example, recall when the two threads were able to execute both their instructions consecutively for updating the queue as well as incrementing the next slot. When both these instructions were executed consecutively by a given thread without interruptions, there was no problems. Only when a thread was interrupted between the two instructions because of, let's say, context switch, there was a problem. So given this behavior, such bugs are very hard to reproduce or detect and debug. So well, how can we fix the problem in the previous example? Just as we have seen, if somehow we can ensure and allow the two threads to execute both these instructions together without any interruptions, then there is no problem. This requirement that an operation or a set of instructions they execute either completely together or not at all is known as atomic operation. In our previous example, if we are enforcing the requirement that both these two instructions inside each thread should either execute completely together, one after the other, without interruptions, or none of these two instructions should start executing at all, then these two statements would comprise an atomic operation. So by definition, an operation that is guaranteed to be executed completely without interruptions or not at all is known as an atomic operation. At the hardware level, an individual assembly instruction is atomic. So for instance, if you have this ANA instruction, let's say add R1, R2, R3, this is an atomic instruction. It would either be executed completely or not at all. You cannot execute it halfway and then leave it. That is not possible. So at the hardware level, it is safe to assume that an individual assembly instruction would be executed atomically. Now at the software level, the operating system may provide services that would be considered to be atomic. We'll talk more about this later. Now let's think about whether this C++ statement is an atomic statement. Note that this C++ statement, when it is compiled, it is actually going to be broken down into several assembly statements or assembly instructions. It is not going to result typically in a single assembly instruction. Now a set of assembly instructions are not by default atomic. An individual assembly instruction is. And therefore this C++ statement is not atomic. In general, when you're writing C++ programs and you would like a certain operation to be atomic, never make an assumption about how many assembly instructions this particular C++ statement would be broken down when it is compiled and translated. If you are expecting a certain operation to be atomic, then you should use the appropriate operating system primitives to enforce this atomicity.